Hi everyone. Today we're going to talk about solving systems by graphing. Systems is just two or more linear equations put together. So solution is an ordered pair that makes all of the equations true. So the way that it works is there's two types of systems, consistent and inconsistent. A consistent is one with at least one solution. That's kind of like the normal. Inconsistent would be no solution, which is parallel lines. So first off, we're going to kind of start with just a couple of examples of is the point a solution to the system? So if you look here, we've got the two equations and we've got the point 2 comma 1. In order to prove that that would be a solution to the system, or a point where both of the equations intersect, we have to plug that point into each of the equations. So I'll start by doing the first one here. I've got 1 is equal to 2 times 2 minus 3. So that would be 4 minus 3. So 1 is equal to 1. So that works. And then the other one here, 1 is equal to 2 minus 1. 1 is equal to 1. That also works. So 2, 1 is a solution. It has to work for both of them in order to be a solution. So if you take a look at the next example, we're using the same exact equation. So we know that that works, okay, based on what we previously did. The other one, though, if we plug it in, 2 plus 1 is equal to 4. 3 is not equal to 4. So this would not be a solution. Again, it has to have both of them work in order for it to be a solution to the system because it's where they intersect. It's the point of intersection. So now let's talk a little bit about how to solve by graphing. First thing that we want to do is graph both equations in the same coordinate plane. Then find the point of intersection. And then that point of intersection is our solution. Systems that have one point of intersection are called independent. So we can have something that is consistent and independent. If it's inconsistent, however, as we talked before in parallel lines, then it would not have one point of intersection and not be independent. As we go down through some of these, you'll also find there are other equations that we call dependent. But we'll talk a little bit about them later. Solve the following systems by graphing. Check your solutions. So I'm going to graph these, and when I do, I'm going to put a little color to them. That way you know which is which. Now, if you have trouble graphing these with a y-intercept and slope, might suggest using a table of values. That might be a wise option for some of you that have difficulty graphing. Table of values, remember, is whenever you draw a table and you put x and y in it, and then you choose some values for your x that you plug into your equation. I, however, am going to use slope and my y-intercept. So the way that it works is this is your y-intercept, and this is your slope, which is your rise over run. So I'm going to start at 1, and my rise is 2, and my run, which is left and right, is 1. So I'm going to go up 2 and over 1, 2, right 1, or I'm going to go down 2 and left 1. And I'm going to graph that line. Make sure that you include your line. And then on the other one, I'm going to start at -1, and this time I have 3 over 1, so I'll go up 1, 2, 3, and then right 1, 2, 3, right 1, or down 1, 2, 3, and left 1. So here I can tell my solution. Okay, my solution is where they both intersect. In that case, that's at 2, 5. Because it has at least one solution, it is what we consider consistent. And because it has one solution for sure, it's consistent independent. Right? Now, sometimes your equation's not necessarily in slope-intercept form. If that's the case, you can use one of two different ways. You can either put it into slope-intercept form, which means solve for your y, or you can use your x and y intercepts. I usually stay on the lines of let's solve for y, personally, because sometimes we can get fractions for other things, and then it might get a little bit dicey as to where x and y intercepts are. But it's solely up to you, however you want to do it. So for this first one here, I'm going to do in blue. I'm going to x plus 2y is equal to 4. I'm going to subtract x from both sides. And then divide by 2. And this x over 2 is really 1/2, so 1/2 x plus 2. And then I'm going to graph it. I'm going to start at 2. Now, whenever it comes a fraction, fractions are a little bit nicer to graph because you're going to go up 1, and then because it's negative, you're going to go left 2. Okay? Negative means a negative slope. So whenever you're doing these lines too, you always want to look to see which way your slope is going. Negative slopes, okay? And then you have positive slopes as well. Or I can go down 1 and right 2. And there's my first line. And then my next one here, I'm just going to subtract 3x over to the other side. So I'll get y is equal to negative 3x minus 3. And again, I'm going to start down at negative 3. And I want to go either up 3 and left 1 because it's negative, or down 3 and right 1. So if I keep going from this point, okay, up 3 and then left 1, I will find a point where they both intersect. That point of intersection there is at negative 2, 3. Because they have that point of intersection, or at least one answer, it's consistent. And then because it's for sure that they have one solution, it's independent. Why we would use systems in real life? Well, sometimes we have to model costs and how much we get of something. So in example 5, if you notice, the system below models the cost of taking an aerobic class as a function of the number of classes. Find the solution of the systems by graphing. What does it mean in terms of the situation? Okay, so we have 2 different aerobics classes. We've got first class, which is going to be in blue, and the other class is going to be in green. In real life situations, nothing will ever really be negative. So I'm actually going to cut out all the quadrants that end up being negative and just work in what we call the first quadrant. I'm going to label my graph. So my y is going to be my cost. And then the a is the number of classes. So this first one here, I'm doing blue. I'm just going to go ahead and graph that. It has no y-intercepts. Technically, that's at 0. So I'm going to start at 0, 0. And then I'll go up 1, 2, 3, 4, and right 1 based on the slope. 1, 2, 3, 4, 1, 4. My line's a little wonky, but that's okay. I'm going to erase to there because I don't need anything that is negative. Next up then, I've got my other one here. It's going to start at 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then from there, it's going to go 2 and right 1, up 2 and right 1, up 2 and right 1. If I keep going, 2 and right 1, up 2 and right 1, I might have to go a little bit off the grid or maybe even scale. So my next one will be 4. And then over 1, I should hit that same point, which in this case is going to be at 1, 2, 3, 4, 5. And then it will be at, so if this is, let's see here, this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it'll be 20. So that will be my point or my solution. What this means in this terms, some of you might go work out at a gym and you might have always thought, hey, I need to switch gyms, but I don't know if I want to go through the cost of like the new startup fee or the new, maybe it's a higher, but then it says that there's no startup fee. This technically says that no matter which of these two gyms I go to, the cost will be the same for 5 classes. So for 5 classes, the cost at either gym is $20. After that, if you decide to take a 6th class, you might want to decide or check and see which one's going to be a little bit cheaper. But for at least 5 classes, they should both be the same. All right. So earlier I talked a little bit about something called consistent, and we also mentioned something about inconsistent. So there are 2 special types of systems that we have. The first one is parallel lines. Parallel lines create a system that is inconsistent because it will have no solution to it. And then we have another one where the line that we graph from one equation and the line that we graph in the other equation are the same. If they're the same line, there's infinitely many solutions. We call this dependent inconsistent, or consistent dependent, as you'll hear me say. Let's take a look at example number 6. I'm going to graph each of these. One of the biggest ways to determine if they're parallel, which in this case they are, is the slope. Same slope means parallel lines. So looking at this, if I graph, let me graph, start at 2, go up 3 and write 1, down 3 and write 1. So here's my first line. And here's my second line. Start at -2, up 3 and write 1, write 1, down 3. Okay. Yeah, the same slope, so you'll notice that. You'll notice that they don't intersect at all. This is going to be called no solution, because a solution is where they would intersect. We'd also say that this is inconsistent. Right, and then solve the following by graphing. One of the equations is already in y equals mx plus b form, which is nice, or slope intercept. I'm just going to create this one into it too. So I'll subtract 3x. And I'm sure that most of you can probably see here. I'm going to divide by 4. -3/4 x. 12 divided by 4 is 3. And these two equations are the same. So this is actually going to present the same line for us. I'll start at 3. I'll go down 3 and right 4, or up 3 and left 4. I only have to graph it one time because it's the same line. When it's the same line, we say that this is infinite solutions. And it will be consistent because it has at least one answer. Because it has more than one answer, instead of independent, this is called consistent dependent type of solution. Right? Now, the best part about a video, if you miss something, there's always a pause button, there's a rewind, there's a fast forward, okay, if you want to check anything. But that's it. That's all I've got for you today.